Okay, so now we know the distance from each seismograph, but what about the direction of the earthquake from the Earth? Yeah, from each seismograph. So the epicenter of the earthquake could be in any direction from the seismic station that recorded the arrival of the waves. So using a method called triangulation, we can determine the location of the epicenter if we know the distance to it from at least 3 measuring locations, 3 different seismographs. So one observation is going to tell you how far the epicenter is from it, and this gives us a radius to work with. So this is going to be the radius that we are working with. This is the observation location, and this is all the possible locations where the epicenter could have been based on this one location. Another observatory is going to narrow our options to 2 different locations. So this is our other hypothetical seismograph, and these are all the possible locations of the earthquake based on it. There are 2 main points where the 2 circles meet, and so those are 2 possible locations for the earthquake to have occurred. And then a third observation can locate the epicenter of the earthquake by the triangulation method. So the point where all of the radii will meet is going to be the point at which the epicenter of the earthquake occurred. So using the same principle that I just explained with the example from above, if we use those distances which we calculated using the travel time graph of last slide, again those distances being 3,700, 4,400, and 2,900 kilometers from the 3 locations listed respectively in the last slide, then we see that the epicenter was somewhere in the western US. So somewhere close to Nevada, Utah, Arizona, kind of where all of these 3 states meet. Okay, so again, from Nome, 4,400 kilometers, that's the circle around it. From New York, 3,700 kilometers, that's the circle around it. So there were 2 possible locations, and then once we have the seismogram from Mexico City, we determined the distance of the epicenter from it was 2,900 kilometers. Where all of those 3 circles meet, that is the epicenter. And it's called triangulation because it forms a relative triangle between the 3 observation locations. All right, so now we know how to locate an earthquake, but how are the sizes of earthquakes determined? So this is done based on intensity and on magnitude. So an intensity scale uses observed property damage to estimate the amount of ground shaking at a particular location. Magnitude scales, which were developed a little bit more recently, use data from the seismographs to estimate the amount of energy that has been released at an earthquake source. Okay, so one is based on property damage observations, and then the other one on overall amount of energy that was released. So for intensity scales, until about the mid-1800s, historical records provided only accounts of severity of earthquake shaking and of the destruction from this. It was after the Great Italian Earthquake of 1857 that a map recording the aftermath of this earthquake's destruction was done throughout the whole country of Italy, and that the method of different intensity areas was developed. So using this method, zones of intensity were made. So with zones of being of highest intensity located nearest to the center of maximum shaking, and often, but not always, near the epicenter of the earthquake. So in 1902, Giuseppe Mercalli developed a more reliable intensity scale, which is still used today in a modified form that uses California building codes as the standards, or California buildings overall as the standard. So this is called the modified Mercalli intensity scale. That is the one that is used today to check the intensity of earthquakes. So this scale is based on the 12-point Mercalli intensity scale, as you can see in the table on the slide. So, for example, in an earthquake that was felt by all, where many people were frightened and they ran outdoors, where there was some movement to heavier furniture, and some small damage to chimneys and very slight damage to everything else, the intensity for that earthquake would be of 6 out of the 12 points. A similar attempt to this intensity scale is done by the USGS and has been relatively successful. This maps the intensity based on people's response to a "Did you feel it?" survey. So internet users are prompted to enter their zip code and answer a few questions such as, did the objects fall off shelves? So in this case, only people who were relatively near the epicenter are prompted to do so, or people who look up that specific earthquake shortly after it happened. This is how they're able to fill out the survey of, did you feel it? And this appears within the USGS website that I showed you earlier in the lecture, for example. So intensity scales are useful, but they are qualitative, and they have certain bias as they're based on the personal account of those who experienced the earthquake. So there is no certainty that, for example, I think that it was very frightening, whether you can think that it was not as frightening if you're used to earthquakes in the area where you grew up, for example. So it's relatively biased based on the personal account of the person who is experiencing the earthquake and how they feel about it. So in terms of magnitude scales, there's a little bit more accuracy, typically speaking. These magnitude scales attempt to describe, again, the energy that is released by the earthquakes that did not rely on factors such as building practices, which tend to vary quite highly from one part of the world to another. So in 1935, Charles Richter of the California Institute of Technology developed the first magnitude scale, which is called the Richter scale. This one is shown on the picture on the right that you see right here. So as you can see, it is done by calculating the distance from the seismograph. So the distance from the seismograph is calculated, and then the amplitude of the largest waves within the seismogram are recorded. So typically, the largest amplitude waves are going to be either surface waves and then sometimes rarely secondary waves or S waves. So theoretically, the amplitude will decrease with distance from the earthquake. And so Richter developed a method in which if all the equipment was calibrated equally across the world, then the the magnitude representing the energy released could be obtained just from, again, the distance from the epicenter and the amplitude of the waves. So many times, however, the different seismographs will obtain different magnitudes for the same earthquake. And this is perhaps only due to the rock types through which the waves are traveling from a location in the world relative to another location in the world, and not necessarily due to the difference in instrumentation, which can also play a role. So Richter scale is, I should say, logarithmic, in which a tenfold increase in wave amplitude corresponds to an increase of 1 on the magnitude scale. So the intensity of shaking is 10 times greater in a magnitude of 5 than a magnitude of 4. And it's 100 times greater in a magnitude of 6 than in a magnitude of 4. So it is logarithmic. It increases by 10 every number that the magnitude scale increases. So, all in all, the Richter scale is very convenient and is very easy to use. So it's a very, very powerful tool. However, the Richter scale is not very appropriate for describing very large earthquakes. For example, the 1906 San Francisco earthquake and the 1964 Alaska earthquake have roughly the same Richter magnitude. But based on relative size of the area that was affected and on the tectonic changes in both of those cases, the Alaska earthquake released considerably more energy than the San Francisco earthquake of 1906. So, the Richter scale is very useful for medium magnitude earthquakes, and it is pretty cheap, but it is not so accurate for larger magnitude earthquakes. So, for measuring medium and larger earthquakes, seismologists now use the moment magnitude scale. So this one estimates the total energy released during an earthquake, and it is calculated by determining the average amount of slip on the fault, the area of the fault surface that slipped, and the strength of the faulted rock. So this moment magnitude scale can be calculated by modeling data obtained from seismograms, but it typically is much better if analyzing it based on all of the properties I just said. So again, the amount of slip of the fault, the area of the fault surface that slipped, and the strength of the faulted rock. So in both the Richter and the moment magnitude scales, each unit increase equates to roughly 32 times more energy released. And this can be seen in the graph that you have on the top part of the slide right here. So this is what you're seeing. The difference in magnitude number is going to experience a very different change in energy that is being released and a difference in ground motion. So again, this is the logarithmic scale kind of idea in terms of ground motion, and this is the energy release increase. So using the moment magnitude scale, some of the larger earthquakes that happened in the past, like the San Francisco earthquake of, again, 1906, or the Alaska earthquake of 1964, or the Chile earthquake of 1960, were all recalculated and are now labeled with a more accurate number, representing the amount of energy that was actually released at the earthquake's time. So the moment magnitude scale is harder to calculate than the Richter scale, but it is also more accurate for larger earthquakes. But it's also a lot more expensive to do. So overall, there are good things and bad to each of the scales, or the magnitude scales, but together they make very great tools in terms of determining magnitudes for all the earthquakes in the world. So a few of the examples of those earthquakes is seen in the graph here on the right. I just want to point out, for example, the Chile earthquake, which is the largest earthquake recorded, had an energy release of 9.5, had an energy release of about, I don't even know how to read that, 56,000 trillion kilograms of explosive equivalent, which is crazy. So, and the same thing happened with the Alaska 1964 earthquake. Close to that amount of energy was released. So, check this list out. Kind of gives you an idea of how strong these earthquakes really are and what kind of damage they can cause.